Now, when you're talking about electrical circuit normally involves a charge that moves through a circuit. It goes around in a loop. All right. So there are comparisons that you can make between the flow of charge in an electrical circuit with the flow of water inside a pipe system. Okay. You can make some similar comparisons. So let's go with something that's more familiar first for the case of water flowing through a pipe system. So let's just say right now we have a pipe system that looks like this, and there are three different levels: level A, level B, and level C. And then we start from here. Okay. So what we'll say here is that whenever you have water at levels A, B, and C, either here, here, or here, they will have different values of GPE because you understood that they are at different heights. So if you have water that flows from A to B and then from B to C, what will happen is that there will be decreases in GPE because there's a decrease in height. The water is actually losing energy here. Now, the fact that that water, or rather that mass of water, is losing energy, that one is actually comparable to PD in an electrical circuit, which we will see later. Okay. Now, at the bottom, when water is pumped back from level C back to level A, there will be an increase in GPE here. The water will actually gain energy as it moves from C back to A. In order for it to move from here to here, you need to put energy in. The water is gaining energy, and that energy that is gained is actually converted to increases in GPE. Now, this one will be comparable to EMF inside a circuit. All right. Now, the flow of water inside the pipe is comparable to flow of electrical current. Any obstructions in the pipe that slows down the water flow is comparable to electrical resistance. All right. So this one is what you expect to see for water flowing inside a pipe system. So now, if we look at the case of electrical circuit, specifically for the case of a charge that is flowing through an electrical circuit, let's just consider you have a charge of Q. All right. So that charge of Q will actually move through your circuit like this. Oh wait, sorry, this is not a good color to use. That charge Q that you have will move through the circuit like this. All right, it will move around the circuit, making one loop, and then come back to the battery. So what we'll say is that the charge, once it passes through the battery, it gains electrical energy when passing through it. This causes it to have an increase in electrical potential. All right, kind of like the case just now when we say that your water, when it went from the bottom to the top, there's a gain in gravitational potential energy. So over here, when your charge went through the battery, there's actually a gain in electrical energy, which causes its electrical potential to increase. All right. Now, as it moves through the circuit, what will happen is that, assuming that no resistance is encountered, note the potential remains unchanged. So what we mean by that is that if, let's just say, the charge was here, and then after that it moved past the battery, it already gained electrical energy. All right. So this charge here is at a certain potential. Now, provided that when it moves from here all the way to here, there's no resistance, we'll say to you that the potential is constant. All right. So over here, it's already mentioned that once the charge passed through your battery, it was already at a potential of 12 volts. So from here all the way to before the resistor, assuming that there was no resistance, the potential ought to remain constant. All right. It's only when it encounters some sort of resistance, like going through a resistor, that your charge will start to lose electrical energy. So your charge moves from here to here. It already gained electrical energy here. The energy that it has remains constant all the way to here. But then once it wants to pass through the resistor, it will start to lose electrical energy. Okay, you start to lose electrical energy, which in turn causes it to have a decrease in electrical potential. So if before the potential was 12 volt from here to here, suddenly over here you start to lose electrical energy. You start to lose electrical energy, you will have a decrease in potential. So your potential will drop from 12 volts to 4 volts. Okay. Then after that, your potential remains constant here. And then once it goes through your resistor, again, it loses electrical energy. You lose electrical energy. Electrical energy is lost. So but again, your potential drops. So after you pass through the second resistor, your potential is actually 0. Then it remains that way all the way to the start of your battery. Okay. So one thing to note here is that when it comes to differences in potential, EMF is the difference in potential between 2 points where charge gains electrical energy. It's actually this part here, which you will normally term as EMF. It's because between these 2 points, the charge is gaining electrical energy. Other forms of energy are converted to electrical, which in turn corresponds to an increase in electrical potential. Before your charge went through your battery, it was at 0 volts potential. But then after it went through the battery, the potential increases because it gains electrical energy. So your potential could have increased to 12 volts. But then when you look at the difference now between these two potentials, this is 12 volts, right? This is your EMF, okay? The same thing could also be said for PD, all right? PD is difference in potential between 2 points where charge loses electrical energy, corresponding to a decrease in electrical energy. So if you look at PD, that one will be these portions here. So when the charge was here, it was a potential of 12 volts. But then once it passed through the resistor, it lost electrical energy. It was converted to heat energy or heat dissipation. So when the charge came out of the resistor, it already had decreased potential due to the fact that it lost some electrical energy. So the potential is now 4 volts. All right. So these two differences in potential is actually what you know as PD. Okay. The same could also be said for here. This one is also PD. All right. PD, EMF are basically just differences in potential between 2 points. But one is different in the sense that if it gains electrical energy, which causes it to gain electrical potential, that is EMF. And then the other, if you see that there's a decrease in electrical potential due to the fact that it lost electrical energy, that is PD. Okay, so this is what in simple terms happens to a charge inside your circuit. All right, so now we go back to page 1. All right, page 1. Now, we'll go through all the different terms like current, voltage, and resistance. Now, the first thing you would learn is current I. All right. Now, when you're talking about current, before we go to current, we need to talk about charges first. Now, all charges that exist naturally are actually whole number multiples of an elementary charge, E. An elementary charge E is 1.6 times 10 power 19 coulomb. Now, all charges that you can see occurring naturally will always be whole number multiples of an elementary charge. What it means is something like this. Your charge could be, say, 1.6 times 10 power minus 19, or 3.2 times 10 power minus 19, or 4.8 times 10 power 19. You see, in terms of the elementary charge E, this one is E, this one is 2E, and then this one is 3E. Okay, whatever charge that you see existing in nature, they must be in terms of whole number multiples of your elementary charge. If say, for example, I have a charge where it is, say, 2.8 times 10 power minus 19, or something where I say it is 6.0 times 10 power minus 19, in terms of your elementary charge, All right, this is 2.8. Okay, 2.8 is actually 1.75 of E, and then 6 is actually 3.75 of E. So in cases like this one is not possible. Only this one is possible. This one is considered whole number multiples of E. All right, all charge that exists in nature must be in whole number multiples of E. All right, they cannot exist in fractions like this. This is just not possible. All right. All right, so this one is actually what you will learn this as quantization of charge. This is known as quantization of charge. Sometimes your exam question, they will ask you, explain what is meant by charge is quantized, or what is meant by quantization of charge. Quantization of charge actually just means this. All charges are actually just whole number multiples of an elementary charge. Okay. Now, then we move on to another thing, specifically to current. Now, if you have a flow of n number of charged particles or charge carriers, where each particle carries a charge of Q, the total charge carried by the particles will be Q, capital Q. Okay, there's a small q here and a big Q here. This small q here is the charge carried by one particle. The big Q is the total charge carried by all the particles. All right, and your number of particles is n. All right, now these charged particles can be electrons, protons, or alpha particles. When these particles form a net flow, if you have a net flow of charged particles in a particular direction, what we will say is that you have current. You must have a net flow of charged particles in a direction in order to say that there is current. Now, current is defined as the rate of flow of charges. So I is total charge divided by time taken. And then just now I mentioned that total charge Q is actually the charge carried by all the particles. So you take the number of particles n multiplied by the charge of one particle. That's why you get nq here divided by t. All right. Now it's from this expression here that you will be able to find something called the number of charged particles per unit time that is flowing. So what you do is that you are actually just looking at I equals to nq over t. You rearrange it, you get n over t, I over q. All right, this one will give you the number of charged particles per second. Right, because n is number of charged particles, t is time. So this is number of charged particles per unit time. All right. Now, if your current is constant, charge is QIT, taken from here. All right. If you want to find out the amount of charge, provided the current is constant, Q is IT. Now, it's from here that you can define your coulomb. All right. Charge is measured in coulomb. Current is measured in ampere. And then time is measured in second. You could say that 1 coulomb is the charge that flows past a point when the current of 1 ampere flows for 1 second. All right. Now, on the other hand, if your current varies, Q is not IT. Okay, here we say that Q is IT when current is constant. If you encounter a case where current varies, then Q is actually the area under the IT graph. What we mean by that is this. If let's just say that you have a graph of I versus T that looks like this, all right, if you have a graph of I versus T like this, you see that the current is varying, it's not constant. In cases like this, your charge is the area is actually half IT. This one is not non-constant current. All right, if you have constant current, okay, you have constant current, you get something like this, I versus T. Constant current would mean something like this. Okay, it's actually also still the area under the graph in general, but here what you get is Q is area under the graph is actually just IT. That's why we can say that only for constant charge, sorry, only for constant current, that charge is IT. If your charge, if your current varies, like this one, you would have to take the area under the graph. Right here, this one is a triangle. So you can actually find the charge as area under the triangle. Or if let's say we give you something else that's a bit different, like this, I versus T, and we give you some sort of regular shape like this. This one you cannot really calculate it out. This one, Q is just area under the graph. Okay, so this one you will normally see more under the very old past years. This one I think is before 2000s. The recent ones don't normally test this anymore, but it's still something you need to know. Okay, right, so this is current. Now we go to direction of current flow. So I'll clear everything here. Right, now when we say current flow in the chapter, the current flow that we're always talking about is conventional current. All right, conventional current always follows the direction of flow of positive charges. It's always from positive terminal to negative terminal. All right, it will be useful to know that current always flows from higher potential to lower potential. All right, I think I wrote it here somewhere. Hey, no, I did not write it here. Okay, wait, let me just get this. Let me clear off this thing here. Right, direction of conventional current follows direction of flow of positive charges, which is always from positive terminal to negative terminal. What we'll just mention here is that current always flows from higher to lower potential. Okay, the reason why current will always flow from positive terminal of a battery to negative terminal of a battery is mainly because it tends to flow from higher to lower potential. In AS, you won't really make use of this information, but you make use of this information more in A2 later on. Okay, so if you're talking about conventional current or current right now, we're always talking about the flow of positive charges, which is from positive terminal to negative terminal, or from higher to lower potential. Okay, so we also have something called flow of electrons to consider. But when you're talking about flow of electrons, flow of negative charges like electrons, they will always be from negative terminal to positive terminal. In other words, always just think of this way, always just think of it as this. Negative charges will always be flowing in the opposite direction to conventional current. Okay, conventional current is flow of positive charge from positive to negative terminal. Flow of negative charges like electrons will always be the direct opposite. It will be going from negative to positive instead, or in other words, it's opposite to conventional current, opposite to flow of positive charges. So right here, what you have, if you look at the diagram, this is your battery. Okay, your flow of conventional current is actually from the positive terminal to the negative terminal. So you see it going like this, like this, like this, like this, like this, like this. Okay, this is flow of conventional current. But when you're talking about the flow of electrons, electrons will be opposite. You will see it as these red colored lines here. Okay, they will flow from negative terminal to positive terminal, opposite to flow of positive charges. So this is for current. Okay. Now, from current, you also have some other equation that relates to it, which is this one. I is equals to ANVQ, where we tell you that there's this little v here that is called drift velocity or drift speed. Okay. Now you need to know the derivation of I is equals to ANQV, and this one was added from 2016 onwards. It's actually quite a recent addition to your syllabus. All right. Okay, so let's start with this one. Now, in any conductor, there will always be large number of conduction electrons or free electrons as there are atoms which form your electric current. Now, number density n is the number of free electrons per unit volume. Okay, so when we ask you to define number density, always remember that number density is number of free electrons per unit volume. If you define number density as just number of electrons per unit volume, this one is not accurate. You always need to write the term free electrons, because when you say number of electrons per unit volume only, the electrons could refer to the fixed electrons orbiting around your nucleus and also the free electrons. So it's better to be specific. Just say the free electrons, the electrons that are responsible for your electrical conduction. All right, always remember to add the term free electrons. If you don't, it means that you're saying the electrons here, if you say number of electrons per unit volume, you're referring to both fixed and free electrons. Okay, so you want to single out only the free, you just write the term free electrons. Okay, now this small n that you see here looks like the small n that you saw in the previous page. Okay, bear in mind that this is not talking about the same thing. All right, in the previous page, the small n refers to number of charged particles, but the current one, small n, refers to number of charged particles per unit volume. Which one is it? You will need to read carefully from the question. Okay. In your case, small n is number density. All right. Now, how do you derive the equation I is equals to AN QB? First, what you do is that you consider a section of wire of length L and cross-sectional area A with number density N, for which electron flows through. This is your wire. Okay, it has a length of L and has a cross-sectional area of A, and it has a certain number of it has a certain value of number density. So what we'll say here is that when current flows, electrons will move through the section with an average drift velocity in a time of t. Now, what you need to know from here is that for this given section of your wire, the number of electrons that you could possibly have is actually your number of electrons per unit volume, which is your number density, multiplied with volume. Because you see, n is number of electrons per unit volume. So if you multiply with volume, you're going to get the number of electrons. Okay, so that one is NV. And then from here, total charge would be your number of electrons, which was NV here, multiplied with the charge of an electron Q. Okay. If you want to find out the current through this section, current, as I mentioned, is actually your total charge divided by time. Total charge is a capital Q divided by T. So your total charge Q is given here already. Number of electrons NV multiplied with Q. That's why you get this. NV times Q divided by T. Alright? And volume is actually area times length. If you take the cross-sectional area A, multiply with the length, volume is product of area times length. So V can be expanded to become AL. So you get N times AL times Q divided by T. Then you rearrange one of the things again. N times A times L over T times Q. L over T is actually distance over time. So it's actually referring to speed. So this speed here is actually your drift velocity or drift speed. Okay, so eventually you are going to get I is equals to AN dq. Okay, so this is the equation that relates drift velocity to speed. Now this equation applies to all charge carriers that form a current. It's not just applicable to electrons. It can be any other charge carriers that move. It could be other positive and negative ions also. All right, so it doesn't just apply specifically only to electrons. It applies to other charges too. Can be positive or can be negative. Right, so this one is for current. Okay, then we go to the next property that you need to know, which is voltage V. All right, now voltage are normally distinguished according to the energy transfer that occurs to the charge as it flows around the circuit. This one is similar to what I explained earlier, the analogy just now that I gave you. All right, a voltage where charge is losing electrical energy corresponding to decrease in electric potential is potential difference. Potential difference by right is defined as electrical energy converted to other forms of energy per unit charge. If you are asked to define potential difference, the statement in yellow is the definition to use. This is the formal definition. Okay, electrical energy converted to other forms per unit charge. So PD is energy converted to electrical energy converted to other forms per unit charge. Okay, this one here is not the formal definition. This one is more like for you to understand why is it like that. Okay, so a charge that loses energy corresponding to a decrease in electric potential is potential difference. Now, on the other hand, if you have a voltage where charge is gaining electrical energy corresponding to an increase in electrical potential, that is electromotive force, EMF. Okay, electromotive force, EMF, is defined as other forms of energy converted to electrical energy per unit charge passing through it. So EMF E is equals to other forms of energy converted to electrical per unit charge, right? Again, this is the formal definition that you should use if you're asked about EMF, okay? So as I mentioned to you earlier also, PD and EMF are really just differences in potential between 2 points in a circuit, whereas value of potential is actually value of at a single point. All right. So if we were to consider movement of 1 coulomb of charge around the circuit right now, like this one here, I have 1 coulomb of charge that moves through the circuit like this. 1 coulomb of charge that moves through the circuit like this. So when you have the charge moving through the power supply, electrical energy is transferred to the charge. So this part here is actually here. This part here is where your charge gains electrical energy. All right. Then the charge will flow through the circuit, transferring some electrical energy to the first resistor, and then the rest to the second resistor. So if in the example of the circuit here that you have, when it was at the battery, it gained 12 joules of electrical energy. So as it moved through the circuit, it encountered the first resistor, and then from here, it starts to lose some of its electrical energy, minus 8 joules, okay? So, and then it continued to move until the second resistor here, it lost more energy. This time it lost 4 joules, okay? So during this time when it kept losing energy and gaining energy, electrical energy specifically, that is what causes you to have changes in potential. So what I could say here is that if my EMF was 12 volts, if over here my EMF was defined as, sorry, let me just change the thing later. My EMF was defined as 12 volts. It means that the difference in potential between the 2 points across the battery is 12. So if I want to look at value of potential, this one could have 0 volt potential, whereas this point here could have 12 volts potential. It's the difference in these 2 points that gives me 12 volts. And because between these 2 points, my charge gains energy, gains electrical energy, corresponding to an increase in electrical potential. That is why we call it as EMF. Then as your charge continues to move here, your potential is constant. 12 volts potential is constant. All right, until here. So this one is 12 volts potential again. So once it passes through your resistor, it loses electrical energy, is converted to heat because resistor dissipates heat. It will lose its electrical energy. You will lose electrical potential. Okay, so since here they say that your PD is 8 volts, that means the difference between these 2 points is 8 volts. If this is 12 volts potential, the potential here should be 12 minus 8, giving you 4 volts potential. And then from here, since you didn't encounter any resistance whatsoever, the potential is constant until such a point that you encounter another resistance, which is here. So your charge passes through here, it loses electrical energy again. You will have decreased electrical potential, but how much is it decreased by? You see that here is 4 volts. So if this is 4 volts potential, and the difference here is 4 volts, it follows that your potential here would be 0. Okay, so from here all the way to here, your charge is having a potential of 0 volts. So this is 0 volts potential constant. All right, that's what EMF, PD, and potential actually is. Okay, so the thing that I just explained is actually also kind of explained here. All right, so you move to the next page, page 4. Now, there's this thing about voltmeters that I also kind of need to explain to you. Now, voltmeters, you know, it measures voltages. Okay, that's what we know. Voltmeters measure voltage. But what voltmeters actually do is that they measure difference in potential between 2 points in a circuit. That is what it actually does. It is measuring the difference in potential between 2 points. Okay, and now voltmeters by themselves do not require a current to function. Okay, so a voltmeter usually does not have current through it. If you're talking about an ideal voltmeter is supposed to have infinite resistance so that no current flows through it. Okay, voltmeter does not want current to flow through it. Okay, that is one thing that people need to understand first. Voltmeters do not need current to function. You don't need a voltmeter for the voltmeter to work. Sorry, you don't need a current for the voltmeter to work. It can work just fine without a current. Okay, now that being said, I say that a voltmeter does not need current to function. Okay, it doesn't necessarily always mean that when there's no current flowing, you're going to get 0 reading in your voltmeter. Okay, this one here is actually quite important to know. All right, if there's no current flowing through your circuit, it won't always be the case that your voltmeter reading is 0. Your voltmeter can give you a non-zero reading even when there's no current flowing through the circuit. Okay, so the example to illustrate that will be the diagrams here. So just remember for now, current does not flow through voltmeter, it's not supposed to, and voltmeter is really just supposed to measure differences in potential. Okay, so let's look back at this diagram here. Look at the diagram on the left. You have this circuit here, like this. Okay, we tell you that this circuit has an EMF of 12 volts and a PD of 8 volts and 4 volts. Okay, this one is your EMF, this one is your PD, and this one is your PD. Okay, so I have a voltmeter that is connected across this point and this point. It's measuring the differences in potential here. Since my EMF is 12 volts, obviously it will measure 12 volts. And then you look at the other voltmeter. Voltmeter 1 is connected between these 2 points. It's measuring the differences in potential between here and here. But since my PD is 8 volts, this one, my voltmeter reading will read 8 volts. And then you look at the second voltmeter, it's connected between this point and this point. It's measuring the differences in potential between these 2 points. But then the PD here is 4 volts. So the difference that I measure here must be 4 volts also. Okay. Now, of interest to you is this particular voltmeter. Okay, maybe I use a different color. Use blue color maybe. Okay. Of interest to you is this particular voltmeter. You say where is it connected to? It's connected here and here. All right. Now, in your case here, this circuit has current flowing. Okay, wait, let me just draw the stuff here. This current is okay. This one is a normal circuit that is closed. You have current flowing here. Okay. Now, this voltmeter here, the blue color one, VP, is connected here and here. So, what do you suppose will be the voltmeter reading? Just now I gave you the example where I told you the potentials, right? So this one, the difference is 12 volts potential. Here, maybe I use green. Here was 0 volts potential. Here was 12 volts potential. And it remains constant all the way to here. Okay. It's only after it passes through the resistor that your potential will drop. Okay. So if your PD here is 8 volts, your potential here, what color can I use? Your potential here would be 12 minus 8 giving you 4, right? Here you will have 4 volts potential. Okay, but it will be constant from here all the way to here, right? Because you see you don't have any resistance in between. There's nothing that causes your electrical energy to drop. Okay, so you see here 4 volts, here will be 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 4 volts. Basically throughout this entire length, it's always going to be 4 volts. So if you have a voltmeter that is placed here and here, the differences in these two potential is actually the same. 4 volt and 4 volt, there's no difference between them. So it's just going to be 0 volts. Okay. So after here 4 volts, you have a PD of 4 volts here. You have a difference in potential of 4 volts across here. 4 volts minus 4 gives you 0. So you're going to get 0 volts potential here. And then it will be constant all the way to here. Okay. So now you see there's some contradictions here. There's current flow, but your voltmeter reading is 0. Okay. So now what happens then if I have that same circuit, but this time I do something to it, where I tell you I break the circuit apart. This one, the circuit is already broken in the middle. Okay. So this one is broken connection. Let's just say that this is your broken connection. All right. So now, if there's broken connection here, okay, this one was closed circuit, got current flow. This is now open circuit. Okay, this is now open circuit because there's some broken connection here. For open circuit, no current flows. So here, I know that I have EMF of 12 volts. Okay, no current flows through here. Now, no current is flowing. What would be the readings for my voltmeter? Voltmeter V1, voltmeter V2, and voltmeter VP. And also voltmeter V0. Okay. For voltmeter V0, your difference in potential here and here is actually just going to be 12 volts. Your voltmeter is measuring the difference in potential between your across your battery. All right. So I could say that this one is 12 volts potential, and then this one here is 0 volts potential. Okay. Now, when it comes to your circuit having 12 volt potential here, previously I said that your potential is, if you look at the previous diagram, I said that your potential is only, your potential of 12 volts was only constant up to the point before your resistor, right? It's after the resistor that your potential start to change because you lost electrical energy. Now, in your case here, your potential is constant also. Okay, wait. The potential is constant also, but it will be constant all the way to here. Okay, maybe I use red color to illustrate the point. Your potential is constant all the way to here. Okay, this one will be where your 12 volt potential is constant. All right. Now, why is it that I say that there's potential constant all the way to here? Why isn't there a change in potential across the resistor? It's because you remember how PD is defined. PD is difference in potential between 2 points, where we say that the electrical energy is converted to other forms of energy, correct? PD was defined as electrical energy converted to other forms of energy, or I also explain it as when you have a charge that passes through a resistor and you lose electrical energy, that corresponds to a decrease in potential, right? That difference in your potential is your PD. Now you look at how charge flows. Is there even any charge flowing in the first place for an open circuit? In an open circuit, there's no charge flowing because there's no current flowing. So you're talking about the resistor here right now. There's no charge flowing through it. There's no current flowing through it. So there's actually no such thing as electrical energy being converted to other forms here. No such thing as electrical energy being converted to heat here. So since there's no conversion of electrical energy to other forms right now, your potential by right should remain constant. Okay, so that's why we say here across your resistor the potential remains constant. Okay, so maybe I better just write it here. No current flows through the resistor, so there is no loss in electrical energy. There is no conversion or loss of electrical energy of charge. Therefore, no PD. Okay, there's no conversion or loss of electrical energy of the charge. Therefore, no PD. Okay, therefore, also you can say this lah. There will be no differences. There will be no differences in potential across resistor. Okay, no PD, no differences in potential across the resistor. So now if we ask you what is the value of your voltmeter reading at V1, this one will actually just be 0 volts. Okay. Okay, now then after that we look at V2. Right, we look at voltmeter 2. Now your potential remains constant at 12 volts up to here. If you look at the other side, this part was 0, right? Your potential again will remain constant up to this point. Okay, here we'll tell you that up to here, 0 volt potential is constant. Same reasoning lah, because you see no current flow, no charge flow, there is no change or loss or electrical energy whatsoever here. So you do not have any PD. So PD here would be non-existent. Okay. So no PD, no change in potential. If I have a voltmeter across here, I will be getting a 0 volt. Okay. So maybe it's better I just write out the potential values. Okay. Here is 12 volts potential. Here would also be 12 volts potential. And then over here is 0 volt potential. Over here is also 0 volts potential. Okay. So you see 0 volt, 0 volt, obviously this is 0. 12 volts, 12 volts, obviously this is 0. Okay, now the last one, VP. This one. Now VP is connected across here and here. So remember I said that voltmeter doesn't need current to function. Voltmeter actually just measures differences in potential between 2 points. So for VP right now, which is connected here and here, it is measuring the difference in potential between these 2 points. This one is 12. This one is 0. So the potential difference, or the difference in potential, is actually 12 volts. Okay. So notice the difference here between this one and this one. This one, you have current flowing, but you're not getting any reading in the voltage. And then this one, you don't have current flowing, but you're getting some reading for the voltage. Okay. It's more like you looking at the diagram and seeing how the potential changes. Right? So this is for voltmeter.